So let's look at the special case of antiderivative. Specifically, we want to look at the antiderivative of 1 over x. But before doing that, let's do a review, and we want to do it through an example. Find an antiderivative of 1 over x squared. Okay, so let's change the f of x and change it to the exponent x to the -2. And then from here on, it's very simple. So the antiderivative, capital F of x, the original function, so we have x to the -2 plus 1, and multiply that. The coefficient will be -2 plus 1, and we are using the 1 over n plus 1 times x to the n plus 1 for the antiderivative of x to the n. Okay, so that's what we have. Now that we have this, let's simplify that. So f of x equals to negative x to the -1, okay, which end up being -1 over x. Very good. Once we get that, we're going to add c to it. So that is one of the antiderivatives that we have, as there are many, infinitely many of them. So this is the antiderivative. Now, what happens if we have derivative is 1 over x? So we have now f of x, which is the derivative, is 1 over x. We want to find the original function, capital F of x, okay, the antiderivative. Now, if we follow this rule, you notice that this will not work, okay, because let me quickly write it. So f of x equals to x to the -1, and if you want to do the antiderivative, this would be 1 over -1 plus 1 times x to the -1 plus 1. Well, you've got a problem right here. And this will never ever be, because you cannot have 1 over 0. But remember that this was true. ddx of the natural ln of x was 1 over x. So we're going to use this now. But there is a restriction for the ln of x. X has to be greater than 0. Okay? And it cannot be anything else. However, when you have a differentiation here, 1 over x right there, this one, x cannot be equal to 0, but it can be anything that is greater than 0, or x could be less than 0, negative or positive. But ln of x, x cannot be negative. So there are two ways to deal with that to get the same antiderivative back. So ln of x, natural log of x, is not the best antiderivative of 1 over x because the domain is different. This has to be only greater than 0, but this one can't be 0, but it can be negative and positive. So that doesn't work. We need to come up with another way to show that the new original function, the antiderivative, has the same set of domain as the derivative. Okay, to do that, this is what we're going to do. Now, what if we consider values of x that are less than 0 and use ln of negative x? So what is that? Take the derivative of ln of negative x. Remember, x has to be negative. That means the value of ln of x is okay. We are not changing the restriction. The value, the argument of ln is still positive because negative times a negative is positive. So this one, what we'll end up getting, -1 over x, then times, and then the chain rule says the derivative of negative x is -1, and then your answer will be 1 over x. Okay, so now notice that both of these, ln of negative x and ln of x, both of these are giving you the same derivative, 1 over x. So here is what we need to do. We need to put them together now, and to do that, we're going to go back and set it up as a piecewise function. So this is what you do. So the original function, the antiderivative, let's call it f of x, is equal to two of them. Ln of x, when x is greater than 0 or ln of negative x when x is less than 0. Okay, and another way of writing that is actually this way, if you are okay with that. And this is ln of absolute value of x, because the absolute value of x will give you the two, and there are two possibilities, and includes these two that I just explained, but this is the short form for that. And by the way, in each case you should add c to that, because again, this c constant matters. And so as in here, the top one plus c here and plus c there. So this is one of the three special cases. I'm going to talk about the second one, and then the third one I'm going to do a video on that, so come back to that. But let's go ahead and look at the second special case, and this one you already know. All right, and this one is when you have the derivative of e to the x. Remember the e function, that's the Euler's number e. If you have set up the continuous exponential function at e to the x, then the derivative of that was itself. Okay, we talked about that in another video. I'm going to put a link to the video about this. That means the slope of a tangent line to the curve at point x or a, whatever the point is, it's that function itself. All right, now if you take the antiderivative of e to the x, okay, so the antiderivative e to the x, you will get e to the x plus c back. Okay, and that is another special case, and just have to remember that. And the concept is exactly the same. Remember how we got the value of e. This is a special number, and the number was taken from the, the limit as n approaches infinity of this continuous compound interest formula. But of course it has another utility in calculus. Taylor series is one of them, but this is the value of e, and based on the limit definition, and then you go ahead and when you deal with the derivative, it's itself, and therefore the antiderivative also is itself. But don't forget the constant of integration added to that. All right, that's about it. Until next time, the special case. Check out the next video, and don't forget to do the exercise quizzes that I put on at the end of this unit, and then end of each of the videos, so that you practice, because active rehearsal is an important thing. You gotta do more examples. Okay, until next time.